Let's get started. In this problem, we have two balls, ball A and ball B, which they are impacting each other at this point here. So in this kind of problem, first of all, you need to show the line of impact. How we can find this line? You just need to join the center of masses at the impact location. So as you can see, the line of impact is the same line as the x-axis. So if you have the impact problem and your objects, they have velocities with respect to that line of impact, they are at some angles with respect to the line of impact, then we call this kind of impact as the oblique impact. So in these kind of problems, we are doing 4 steps. First, we need to resolve all velocities along the x and y direction. The next step is to write conservation of linear momentum for system. The third step is to use the coefficient of restitution. This helps me to have one equation for my unknowns. And the fourth step is to write the conservation of linear momentum for each particles normal to the line of impact. So let's see how we can apply these 4 steps. So we know the mass of the particles as a side note, and we also know the velocity of particle A just before the impact. So let me go ahead and find the velocity components along the x and y direction just before the impact. For A, if I resolve the velocities along the x and y direction, these are my components just before the impact. So VAX is in negative I direction, so it's minus VA1 cosine 40, which is minus 1.5 cosine 40, it's equal to minus 1.1491 meter per second. The y component of velocity just before the impact is minus VA1 sine 40, so minus 1.5 sine 40 is equal to minus 0.9642 meter per second. So how about the velocity of B before the impact? If you read the problem, it says the ball B is originally at rest. So both components in y and x directions are equal to 0. So it was the next step for the problem. The second step is to write the conservation of linear momentum for the system. So the system, it has 2 particles, so MA, VA. So which velocity we have here? This velocity is the velocity along the line of the impact. So you need to write this equation along the line of impact. So VAX1 plus MB VBX1 is equal to MA VAX2 plus MB VBX2. So the masses are the same for both particles, so let's get rid of them here at this step. So VAX1 is minus 11491 and VBX1 is also 0. This is equal to VAX2 plus VBX2. So let me call this equation as equation 1. Another equation, so this is a step 2 that we already did. So another step is to use the coefficient of restitution. So coefficient of restitution is always written for velocity components along line of impact. So line of impact here is the xx direction. So please remember that there is no y velocity, y component velocity in this equation. So VBX2 after the impact minus VAX2 divided by VAX1 minus VBX1. So this was equal to 0. You can see that here. VAX1 is also minus 1.4091 and E is equal to 0.85. So let me rewrite this equation. 0.85 times minus 1.491 is equal to VBX2 minus VAX2. So let me call this one equation 2. If I use these two equations, I can find VAX and VBX right after the impact. But how about, so I can find these two, so how about VAY and VBY after the impact? How can I find them? To find these two components along the y direction, I will go through the step 4. So write the conservation of linear momentum for each particles along the normal line to the line of impact. So MA VAY before the impact is MA VAY after the impact. For B, the same discussion. MB VBY before the impact is MB VBY after the impact. So the masses are the same. So here what we have is VAY1 is equal to VAY2. So VAY2 is equal to minus 0.9642 meter per second, and VBY2 is equal to 0. Remember, this one was 0. So this is the y components, and the x components can be also found from solving these two equations. Solve equation 1 and 2.